Yo-ho-ho! Our last element of thermodynamics refers to a theoretical cyclical process called the Carnot cycle that describes the operation of a theoretical engine that operates as you see in this PV diagram. You can't tell by looking at it, unless you're looking just purely qualitatively, that it consists of two isotherms or two isothermic processes and two adiabatic processes. Oh, look, batic. Adiabatic here. Oh, look at this. Adiabatic. You didn't think I would, but I did. Two isotherms and two adiabats. Qualitatively, you should be able to tell that if we look at a point, say, like that, remember we said the adiabat is always steeper than the isotherm going through the same point. So we can talk about each process. I mean, we know things like this. Delta U is 0 for that when it's an isotherm. It expands, and therefore heat must be, or energy must be added, right? So, I mean, why is this a hypothetical? Come on in. Sorry, buddy. Those big and tall Stephen Lawrence Cox, my friends. Anyway, yeah, so think about this being, kind of a theoretical thing. What we're doing here is adding energy, but every single bit of the energy makes the gas expand and doesn't increase its temperature at all. I mean, how feasible is that to do? I don't know. But I can see how that could be, something that we considered sort of hypothetical. Not hypothetical, but theoretical. Best case scenario, we'll say. All right, process B. It's an adiabat. No energy is added at all. This thing does still expand. Yeah, and that means that temperature goes down. I don't know. How the heck does it expand, right? Jeez, I don't know. But temperature drops. Okay. And let's see, process C. Well, I can tell it's an isotherm. It's compressed. Therefore, we're able to take energy out of the system. And that didn't happen. Don't avert your eyes. Don't. Okay. And then in process D, another adiabat, without adding any energy, we compress the gas. Volume gets smaller, and that makes temperature go back up. Up, you say. Up, I say. All right, so there's a lot more to this, folks. How did Carnot come up with this? I'm hesitant to say this on tape, but I have no idea. But what you have to know is that that's what a Carnot cycle is. Two adiabats, two isotherms. And for whatever reason, this also allows us to establish an upper limit for real engine functionality. Okay? We say that this occurs at a temperature we'll call TH, that isotherm. This occurs at a temperature we can call TC. Now, through some miracle of physics, it can be shown that the efficiency of this the efficiency of this cycle, after all, this is an engine. It does more work in the expansion than it does in the compression. Therefore, in total, we put energy in. This is bigger than this. We put energy in, but this ends up doing more work than we do on it. All right, so we dump energy in, it produces work. So we would say this is work over QH, all right, which we can say is, let's see, for an engine, we put energy in, and that we get work done, and we exhaust energy. Okay, so we can write, let's see, W as Q, there it is, QH minus QC, which which you can write as 1 minus QC over QH. Well, for a Carnot engine, there is something called the Carnot efficiency. And what you can do is relate entirely or directly the energy exhausted and added to the temperature of the reservoirs from which and to which those amounts of energy are taken or moved or transferred, I should say. Not moved, transferred. All right, so we can turn this into 1 minus TC over TH. All right, the efficiency of a Carnot cycle has entirely to do with the temperature of the two reservoirs from which energy is transferred, or into which energy is transferred. That's the only calculational thing you need to do for a Carnot engine. Okay, so we see a problem like this. Like this, you say, yeah, there's a Carnot efficiency. There's that. There's that. So we can still do the heat one. We can also do, since it's a Carnot, the temperature one. So here is our, from a hot reservoir, that's our T hot. Absorbs 800 joules of energy, that's our QH. All right, we want the energy expelled, that's QC. This is going to say that QC over QH is 1 minus E, or QC is QH 1 minus E. We want the temperature of the cold reservoir. Well, it can be shown with some algebra. Same thing, just with T's instead of Q's. Okay? So that's really the only thing that you need to be able to do with Carnot engines. All right? Make sure we can talk about Carnot efficiency, which just relates temperatures. Do you want to solve? We don't really need to solve, do we? We can if you like. QC, QH, 800 joules times 0.7. Right, it's 30%. That's 0.3. 1 minus 0.3, 0.7. QC, 560 joules. TC, 500 Kelvin times 0.7. TC, 350 Kelvin. Fair enough? Okay, folks. There's your Carnot. Adios.